The last video in class 19 takes a look at two ways radicals are used in biology. The first example we'll see is the biosynthesis of Icosanoids, which are very important molecules that control inflammation and blood flow. And the second example, we'll take a quick look at the mechanism of antioxidants. Icosanoids are signaling molecules made by the oxidation of 20-carbon PUFAs, such as arachidonic acid. Arachidonic acid is an essential fatty acid, which means that it needs to be obtained through the diet. Humans cannot biosynthesize it. Now, prostaglandins are in the prostaglandins are a subclass of icosanoids, and they're typically found in sites of tissue damage or infection. And here I have listed some processes that it controls. Like I said, inflammation, blood flow, the formation of blood clots, and the induction of labor. So there's a whole class of prostaglandins, and radical mechanisms are involved in the conversion of this fatty acid, arachidonic acid, this is a polyunsaturated fatty acid, into one of the precursor prostaglandins. Now that prostaglandin can be derivatized into other signaling molecules, such as these shown down here. But what we're interested in is this enzyme, cyclooxygenase, or COX-1, COX-2, and the use of two molecules of O2 and how they convert or oxidize AA. Okay, so on the next page I'll go through the mechanism arrows that convert arachidonic acid to PGG2 via this enzyme cyclooxygenase. Actually, this enzyme, you've heard of COX inhibitors like Vioxx. Those were in the news a couple of years ago. And aspirin actually inhibits the production of prostaglandins. So this is a very functional class of molecules. Here I've drawn out arachidonic acid. Again, it's a 20-carbon fatty acid, and in the enzyme cyclooxygenase, we have a tyrosine that is converted into a tyrosyl radical. And what's going to happen is the hydrogen off of carbon number 13 is going to be abstracted by our tyrosyl radical. And then this bond actually starts to make a double bond between carbons 12 and 13. And maybe the best way to do this is like this. And then 11, you share one of its pi electrons to make the double bond to the right, and we put a radical on carbon 11. So the double bond is shifting. Why don't you go ahead and draw the result of how the tyrosyl radical now looks, and also how the arachidonic looks after step 1. This is the result of the first step, where we have a radical at carbon 11. Next, we're using a form of oxygen called triplet oxygen, and it's indicated like this. This is our first O2, and it's a diradical. What happens is one of the oxygens is going to connect to carbon 11. Okay, pretty simple. Let's draw the result of that. Alright, after the second step we have the structure down here. And now we get to use the second molecule of oxygen. First thing I would do is to make a bond between this oxygen and carbon number 9, and we could do that this way. Use this double bond. Okay. The next thing is, what do we do with the second pi electron? We're going to make a bond between carbon 8 and carbon 12. And one way we could draw that is like this. So now we have a pi electron on carbon number 12. That's going to shift over, and we're going to make a double bond between carbon 13 and 14. Next, we're going to make a bond between carbon 15 and the oxygen. And then finally, we remove this this hydrogen, and remake the tyrosyl radical. Now, the way I would try to remember this is make this be your first mechanism arrow, and this is the second, and then it sets off a cascade effect. You are connecting what? You're connecting the oxygen to carbon number 9 and carbon number 8 to 12, and then shifting the double bonds, and ultimately you connect 15 to oxygen, and that will end up being an OOH. Okay, let me draw this for us because there is some stereochemistry, stereoselectivity that's involved. So here's our final product. It's called PGG2. We reformed the tyrosyl radical. Let's see if it matches. It would be, yep, it would be this molecule right here. Let me fix this one stereo center. Okay, and then from there, it can be derivatized into other sets of prostaglandins. The next example that I want to quickly talk about, or briefly talk about, are the antioxidants and the mechanisms. Here I have two antioxidants, a natural one, vitamin E, and one that's used as a preservative in food products, BHT. So an antioxidant is a compound that stops an oxidation reaction from occurring. Like I said, vitamin E is a natural antioxidant. So it prevents radical reactions from happening within the cell that can cause oxidative damage. And this oxidative damage is connected to aging. So many anti-aging formulations contain antioxidants. Now, BHT is a synthetic antioxidant called butylated hydroxytoluene. You'll see BHT in, you'll see that as an ingredient in bread, and it prevents spoilage. The mechanism is pretty easy. It requires the phenol group of vitamin E or BHT to react with an oxidant, or a free radical, and the resulting phenol radical is very stabilized, and it doesn't participate in any propagation steps. So I have that bulleted here. To terminate radical chain mechanisms, both vitamin E and BHT used a phenol group. The phenol group looks like this again. So the radical, let's say we have a free radical in the body. We can just represent that with an R, like that. And the antioxidant, the job is to prevent this from participating in any propagation steps that could be damaging to tissues. And you know the mechanism. We go like this, and we form the phenolic radical. So this RH is pretty much unreactive, and same thing with the phenol radical. Okay, I'll draw the other electrons to lone pairs. Now, there's resonance involved with this. We haven't really talked about resonance of radicals in this class, but what can we do? We can, let's see, we can take this unpaired electron. Oops, that should be a fishhook. Okay. And we take this one electron from the pi bond, make a pi bond between the oxygen and carbon, and put a radical directly on that carbon. And we have this. And obviously you could go around the ring. You could practice that. Such. Etc. Effectively, this antioxidant has stopped any propagating radical processes that can occur in the body.